numeric ones. For example, initial conditions. And, it's very well explained how initial conditions are set up. Everything, all this is explained carefully. All the details are explained carefully. How you construct the dimensionless time, and then how you compute the present cosmic time in the new, how do you define the initial value functions. It's all explained in the file, so I'm not going to go further. See, they need, you choose the standard density and standard curvature, and then the procedure computes the quasi-local quantities by numerical integration. And it's everything explained here. This is a Maple code that is commented. All these green things are commentaries to tell you what the code is doing. But you don't have to worry about that, because Maple simply will execute the code, and then it will save some global variables that you can use after running the worksheet. If you save it with a save statement, then the next Maple session you read the file that you saved, and then the global variables will be, and then you execute the program, then the global variables will global variables will be defined, and let me just show you how it works very quickly. This is a new file. See, can people see this size of letter, or want it larger? Make it larger. Okay. So this file will read the other file and execute it. See? First, sorry. You read the other file, and then the file has this information, and then this is an example of how you use this initial conditions file. There is an example here. Suppose you define your initial functions in this form, then you have 3 free parameters, and this is the way you would access it. This is exactly the syntaxes. Anyway, you have to read carefully. There is, as a first example, we take dust in a lambda CDM background, and this is the way you execute this thing. And here is all the information you get. The radial read, there is all values, like 50 values between 0 and 2. Maple generates them, and then it gives you the list. The list of the mass and special curvature for these values, the value of lambda, and then all sorts of plots. These are the plots of the initial conditions. And then once you have that file charged, then you have to integrate the differential equations numerically. These are the differential equations, and this explains to you how to integrate them. These are the equations themselves, and this is the instruction that will integrate them. It's a dissolve instruction with these options. Once you do the integration, you assign names to the numerical functions so you can manipulate them as normal functions. This is all explained here. Here you know how to evaluate them. This is, for example, the density for this value of the radial grid at this time, you evaluate it like this. It shows you, it explains how they are evaluated. And then how they are plotted. You plot them like this would be the logarithm of the quasi-local density for the grid value number 27. Because of the homogeneity, the density behaves differently for different grid values, right? And here is the function gamma. You can plot them. You can plot them as you plot any function. And then more things. Now here you can generate this type of three-dimensional plots, which show you the time, the radial grid, and the function gamma. You can plot it in this way. It's a collection of space curves. It's a sequence of space curves. Each curve corresponds to a value of the radial grid. And then you can also generate animated curves like this. It is telling you the value here, the value of the radial grid, and here it's showing you, it's a function of time for different radius, but you can, here you can see it, right? This is another way of displaying this information. It's also very, very useful. This is the files that I'm going to give you for numerical work, right? And in different functions, you can plot them either as three-dimensional, or you can plot them as animations of this type. You can run the animation fast, or you can also see square by square, picture by picture. And this, for example, is this is a quasi-local density, say, and the local density, they are very similar. One is in red, the other is in, they are very similar. Okay, so these are all sorts of graphs. Like this one is one. I did more graphs so that you have more examples. So, as opposite to what I presented yesterday, this has short explanation and lots of examples. Right? This is a three-dimensional graph, and this would be the equivalent graph in animated form. Okay? So all these things will be at your disposal. You can use them as templates, and if you have any doubt, you can always send me an email. Okay, these are all the different graphs that you can get. So now let's go. Let's go to the material we're going to see now. Continue with the course. We're going to see now basically two things. The models, as I'm going to do a quick review of what we've seen, but then the important thing is you see that the models using the quasi-local scalars can be described as exact perturbations, and then that you can also construct dynamical systems with them. And you can use this description to study two phenomena. This I don't know if we'll have time to see today. One of them is for example, the issue of the back reaction. I'll explain what's that. And also, it's very interesting that with the quasi-local scalars, you can study asymptotic properties of the models, and also you can study the type of, for example, is it so that if you prescribe an initial overdensity, will this density profile will be preserved by the evolution? We'll show that not necessarily. You might have an initial overdensity that becomes a density void. It's a generic possibility also. Okay, so they say that you cannot teach new tricks to an old dog, right? It's commonly said. It's an old dog, you are teaching new tricks to an old dog. Right? So, who said you can't teach an old dog new tricks? You can. It's not true that you cannot. The truth is you can teach any old dog, you can teach new tricks, right? So, now there's this fellow it's telling you that who said you can't learn new tricks from an old solution. See, and the point is that LTV models were discovered in 1930, right? And they were rediscovered several times. And then they were rediscovered more times. And because in those days communication was poor. So somebody by the name of Dutt, working in India in about 1931 or something, discovered the models. He didn't realize that Lemaitre had discovered them before. And then Tolman came back to them in 1934, and also he thought he had discovered them. And then in 1947, Bondi also came out. I don't know if Bondi cited those people, but
Bondi
cited them.
Yeah, even Tolman cited. Not Tolman was also citing Lemaitre's work.
Yes,
yeah.
they cited.
Yeah.
Okay, but anyway, these are old solutions. 1930. That's when my mother-in-law was born. She's an old fag. She's an old bag. Sorry, she's an old bag. She's 85 years old. My mother-in-law was born in 1930, and now she's a senior lady. Now, these solutions are as old as my mother-in-law. They're quite old. So, how come we still study them? Don't we get tired of them? And the point is, we can always learn new tricks from this solution, right? Okay. So, and then what are these new tricks? We'll see some of these new tricks. Like, for example, LTV models can be conceived as exact covariant non-linear perturbations on an average FLRW background. So as you saw, the Q-scalars are related to an average. That's not the standard average. It's just an average with a weight factor, right? But this average, remember that Q-scalars identically satisfy FLRW relations, but they are not FLRW objects. So they are, from all the scalars you can construct with an LTV model, the Q-scalars are those who satisfy the scaling laws and time dynamics of FLRW models. So they define a sort of background, and then the models behave like perturbations around that background. We will see that. Now, another thing, we can use these scalars to study the models as dynamical systems. We can also study the evolution of the radial profiles, asymptotic properties, and we can use this description to probe, to explore theoretical formalisms, which there are averages, back reaction, effective acceleration, that's Buchert's average, entropy proposals, etc., etc. Right. So these are the new tricks that we're going to see, and especially now that we've already gone through the models. So a lot of what is coming now is going to be a review of what we have seen. example, we have seen them in their standard variables. Here I'm using a notational change. It's, yeah, K was here. But it doesn't matter, it's just notation. But you've seen this representation. I'm not going to stop here, and I'm going to go fast because this is a review of what we've seen, okay? Then the field equations have this form with a for velocity that is comoving and geodesic, and we obtain this sort of Friedman-like equation of state, which we integrate. I'm taking the case lambda equals 0 for simplicity. Okay, we can integrate this. We've seen that. That this has some solutions, some analytic solutions, and of course we also obtain this. This follows from the field equations, as we have seen. So we can integrate this equation. We can integrate provided there is a symmetry center that will give a, well, we can always integrate, but if there is no, if the lower bound of the integral is not 0, then we get the upper bound minus the lower bound. So that's the difference. Okay, so we have these three parameters now, and once we prescribe these three parameters, we integrate these things and we obtain all the quantities we need. We've seen them. Okay, I'm going fast. Now, standard kinematic classification, we've also seen the models can be hyperbolic. Here, remember that we had K negative, and here was K positive. This is K equals 0, it's just a change of notation. And then this is a Friedman equation. We saw that some models can be perpetually expanding. They can expand and collapse, or they can have regions in which there is expansion and collapse. Okay. Now, we've seen that, so I'm not stopping. Now, LTV models can fit supernova data and provide an alternative to the lambda CDM model. Well, now we know. I should have put a question mark here. Can they provide? Really, they cannot, because the models are too simple. They can you can use the models to explain the supernova data. You can also explain a few other observations with the models. But there comes we have now so many observations, so many cosmological observations, and the observations have to be satisfied, all of them. You cannot say, well, the models satisfy the supernovae data, but they do not satisfy the CMB or BAO or Hubble flow or measurement of the Hubble constant. Because then if the models don't satisfy all of them, then they're not providing an explanation. See? It's as if I have a gravity theory, and I can explain solar system experiments, but I cannot explain galactic dynamics, and there has to be something wrong with the theory, right? Or vice versa, I can explain acceleration of the universe, but I cannot explain black hole physics or solar system. Then that theory shouldn't be correct. Because, okay, you can always say, well, gravity near the black hole is very different from gravity at the universe. And that is possible, but it is always preferable a universal gravity theory that can explain gravity everywhere. Now, if you say, no, gravity is different at different scales, then you are adding new parameters, and then that is a more difficult and risky path. I'm not saying that it's not possible, but nevertheless, can they fit? What I'm going to explain is why they can fit supernova data. See, this is important because we've seen theoretical properties of the models, but I would like you to feel a connection also with observations. So why can these models fit this? Now, point is, the light cone structure is much more complex than in an FLRW model. And here, there is an important point. Like, what happens with observations? Thank you. What happens with observations? So, let's suppose this is our world line. Let's suppose that we live in an FLRW model with perturbations. Small perturbations. And here we are, this is our cosmic time. There is a supernova here. This should be straight. This is a supernova, and this is us, right? Not the United States, but us, right? Okay. So, there's a light cone here, right? We see the supernova, we get light from, this is our light cone, right? This is our light cone. We see the supernova, and the light cone, what is the light cone? It's a null geodesic. It's a null geodesic. The tangent vector to this null geodesic, it has to satisfy this condition. Right. It's a null geodesic. Therefore, it's a curve with zero length. Okay? And then it also has to satisfy this condition. It is a curve with zero length, but it's a geodesic. Anyway, you can always prove that curves with zero length are always geodesics. And these are called null geodesics. Right? Now, look how this is what I'm writing here is this. Right? You have this line, this curve, is a solution of this equation. See? And it is a solution that it involves the metric directly. Right? Once we have the metric, which is a solution of the field equations, we will have a curve. Okay? Now we also know that the universe is expanding, right? So this supernova, we will associate a redshift to this supernova, right? Okay? We see supernova, anything we see, we observe, we assign us, we observe an associated redshift. Okay? Now, why I'm talking about a supernova and not a galaxy? Because for very far away galaxies, the only thing we will detect is a supernova. Supernova is a star that is as bright as a full galaxy. It's a very, very special stars. It's like if you are navigating, okay, at night. You're navigating at night in a ship. So boats, the small boats that are around you, you can see their lights. But because these boats are very near you, you can see every light in the boat. You can see the bulb in the kitchen, the bulb, etc., because they are very close, right? And the bulbs are not very, very bright because they are very close, you see them. Now what happens with ships that are very far away? First, you cannot distinguish individual lights. You only see a bunch of light. And second, if the bulbs are not bright, it will be faint. Okay? Now suppose you handle to these boats, to some of the boats, you manufacture a huge bulb, a bulb of 1 million watts, right? But you manufacture, so you know exactly that this bulb is 1 million. And you give this to different ships. And the ships go on, right? So you know that those ships who have this type of bulb will be visible, even if they're very far away. Now you're not going to see the ship, you're just going to see the bulb. And you are not going to see individual small lights in that ship. If the ship is very far away, the only thing you are going to see is the bulb that you gave them. Now, because you know what type of bulb it is, you can estimate the distance of the ship by how much light it is, right? So this mechanism is called, these bulbs are supernova. And the supernova, the fact that you know the intensity, the absolute intensity, because you made this bulb. This means that the bulb is a standard candle. It's called a standard candle. Now, in cosmology, we did not manufacture the supernova. We did not have a workshop and say, hey, okay, let's go and build a supernova. Okay, bring me the screwdriver, the hammer, we're going to build a supernova. It's not like that. We did not manufacture the supernova. But we know the physics of the supernova sufficiently well in order to estimate that most supernova of type 1A obey very similar physical principles, therefore they must be very similar to each other. We know they're not identical, they're not identical twins, but they're fairly similar. So this works as the bulb that I'm distributing to the ships, right? So all what we see is supernova. Now, let's say this is one supernova, and this is the world line of another that is closer, right? Let's call this supernova 1 and the supernova 2. And so we assign a redshift 1 and a redshift 2 to them, right? Okay? The further away is the supernova, the larger is the redshift, right? So we can say that this curve is parameterized by redshift, right? This curve, in general, this curve will be parameterized. This Ka will have a component, let's say Kt, that depends on lambda. No, let's not call it lambda, let's call it V. K, R, V. In general, this curve, this will be a curve that is parameterized by what is called an affine parameter. Okay, theta. If our coordinates are t, if our coordinates are tr, theta phi, these are our coordinates. This vector will be parameterized in this form. It's a standard notation too. This is a parametrization of this vector, of this. Well, let me see. Maybe this is the. No, let me write it this way. Sorry, it's otherwise you'll be confused. Let me write it like this. Yeah, this is a curve. This is a curve. This curve is written like this And the tangent vector to this curve is k. We define k, ka, as exa. This is simple geometry. I mean, please tell me if you don't understand. I hate to talk to a wall. If you don't understand, say, we don't understand, we don't know what you're talking about. Okay, and I'll look for an alternative explanation.
Can you just tell about that figure? The
What?
left-hand side figure, little bit more, yeah.
This diagram?
Yeah.
Well, this diagram is, it's a representation of space-time. Let's say the coordinates t are, this is the axis of t, and this is the axis of r, right? And this is a fixed time surface.
Okay.
And so this is a light ray connecting us to a supernova. Now, light ray is a curve. No? No, why not?
No, yeah, it's
Okay.
yeah.
Because you said no. Okay, so the light ray is a curve. And the tangent vector to this curve
It's clear, okay.
is k. And k has to satisfy these conditions. Okay?
Sir, ये redshift will depend on the distance of the object or the
What?
redshift Z. It
Yeah.
will depend on the distance or the receding velocity of
No,
object.
yeah, it depends, but that's what I'm explaining. That's what I'm explaining. What I'm explaining is that obviously, since we get an increasing redshift for all these objects that we're seeing, as the further away the objects are, the larger is the redshift. And this is something observed. Forget about geodesics or whatever. We know that the further away the objects are, the larger is the redshift.
And
larger-
depending on the receding velocity also, na? If it
Now, forget about that. You just concentrate on this very simple thing. Do you agree that the further away they are, the larger is the redshift?
Yeah.
And that there is a continuum?
Yeah.
Don't complicate your thing. Don't complicate yourself. Don't make things complicated. Just this very simple question, right? Are you agree on that? This means that this curve can be parameterized by the redshift.
Yeah.
Okay? This means, now, we agree on that. We agree on that. Why? Because this curve, here we have z equals 0.001, and it is continuously increasing. For each point in this curve, we have an increasing redshift. Therefore, the redshift can act as a parameter along this curve, right? Is that correct? Okay. So now we go to mathematics. The tangent vector to this curve has to satisfy this equation. Right? Okay. Now, the curve itself will have this form. This is a parametric form of the curve, right? Because here we're only showing t and r, but really the curve, this curve, has a form t v r v, etc. This is a parametric curve that depends on a parameter, not the redshift so far, any parameter.
what is the V?
V is a parameter,
Any? We don't
any
know.
parameter. Well, in fact, and this is where I'm going to go now, we can express the curve in terms of one parameter, so that the tangent vector has this form, and the parameter V such that the parameter such that this holds is called the affine parameter. Okay? Now, we can always parameterize this curve in terms of the redshift. This would mean changing this, making this parameter a function of the redshift. Notice that this parameter is also increasing. It's not the redshift, okay? Now, the redshift is not an affine parameter. It will not have this form. It will not satisfy this equation, but it will satisfy this equation. Something like 5K, 5Ka. It's not a, but it will still satisfy this condition, but it will not satisfy the redshift does not satisfy this because it's not an affine parameter. This is mathematics. If you don't understand this, just keep it as information. Don't try to understand it if you don't understand it. What I'm trying to say is that this curve can be parameterized by the redshift. But if you parameterize it but the redshift is not an affine parameter. So you have to test it with a different equation, right? Okay, but it can be parameterized by the redshift, okay? And this is a fact, an observational fact, okay? So we assign different redshifts to different supernova, and it can be parameterized, right? And the geodesic is a curve whose tangent vector has to satisfy this condition if it's an affine parameter, or this condition if it is a redshift. Okay? So these are the mathematical conditions. Now, let me erase all this with some. Yeah, can I erase all this?
So we are going to define some another parameter.
No. We use the redshift. Just wanted to tell you that the redshift is not an affine parameter.
But you have written V is equal to V of Z, no? That thing?
Where?
V of small v is a function of Z. Yeah.
Yeah, you can always relate them. You can always you can always relate them. It's what is called a reparametrization.
Reparametrization.
Okay. Now, okay, let's raise this. Okay, so the point is that if you are using an FLRW model, you are using a null geodesic, then you will have a relation, you are going to establish a relation between the redshift and the distance, right? Establish a relation between the redshift and the distance. The redshift is given, right? See, the redshift is given. But the distance has to be computed from the redshift. See, what you have is, you have a supernova here, and you know that you are connected with a light ray, right? And so you get a redshift, and you get a distance here, right? You get this distance given by this redshift, okay? Right? But this is for example, for a model, for an FLRW, let's say FLRW model with lambda greater than 0. You get something like this. Okay? Now, remember that this is observed, and this is deducted. This is deducted from the model. This is observed, but this is deducted by the model. See, the model will tell you the null geodesic. Now you change the model. Say FLRW model with lambda equals 0. Say here curvature equals 0. Say curvature is negative. You change model, right? You change model. In fact, we can do it here. We can do it here. Let's change model. We change model, then the geodesics also change. The geodesic equation also change. And then you might get the redshift. See, if you change model, the same observed redshift will give you a different distance because your null geodesics changed. Therefore, if for example z equals 1 for this model gave you this distance, redshift equals 1 for this model will give you a shorter distance or longer, depending on the model, right?
That means, sir,
Yeah.
if we take another model, different models, then we have different redshifts. For the
No.
same-
Redshift is observed.
Yeah,
Okay.
There's a supernova there, redshift z equals 1. That is independent of the model because you observe this.
Okay.
What is depending on the model is to say how far away
Okay.
is that
Distance will
supernova.
be different.
Yeah,
For
that
different
depends on the
models.
model.
Okay.
Because the distance you deducted,
Okay.
right?
So
Based
then,
Okay?
on-
Yes, it's based on the model.
so then
Yes.
sir, how we will say which one is the correct one model?
Eh?
We have two model, one model predicting D1 and
No,
another one
because
D2.
you also have another estimation of distance. That's I'm going there.
Yeah.
Okay, so the model gives you a distance. So the models will give you all sorts of distance. So how do you know which one is correct? Because you have another estimation of distance, which is the luminosity. And this, for example, here in these two models, we have two distances. So how do we know which one is correct? Because it's a supernova type A, we know absolute magnitudes, a standard candle. So we can compare, we can say, yeah, this model gives, the distance given by this model is too short in comparison with the distance we get from the luminosity. So do you see the reasoning? See? Redshift given. The null geodesic analysis will predict the distance. But we compare this distance with the luminosity distance. Okay? And this is how we can discriminate models, right? Okay?
Yes, sir.
Now, what happens in the case of FLRW geometry, what we see is that only that we see with FLRW geometry, we see that if omega, if lambda is 0, then there is a short. Then we cannot fit this process, right? Okay. Now there is a subtlety here, because actually the models give almost identical predictions for nearby supernovae. I'm also going to show that. Also going to explain why. We need, because people ask me why this was not discovered before 1996. Well, it was not discovered because we did not have sufficient reliable information on distant supernovae, only on close ones. And for close ones, the difference is negligible. I'm going to explain why. But the point is, once we started surveying further away supernova, then we started seeing that only the models with cosmological constant were able to fit all the logic together, right? And therefore, these models were favored. Now, what happens? Why? See, here we are, right here, and this is a close supernova that is not very far. This is a distant one, right? So now let's look at the null geodesics for different models, right? Let's say this is a null geodesic for a model with the lambda equals 0, k equals 0, right? Okay. Now we take another model. This is k negative, okay. And then we take another one. With lambda greater than 0. So notice how the not for let's say this supernova Z equals 0.01. And let's say this one is Z equals 0.5. This is quite distant supernova. Okay? This is very close. Very close supernova, very difficult to detect any difference. Right? Only these curves begin to make an important difference once we take far away supernovas. And then what happens is that you get predictions of distance for the same redshift. You get different predictions of distance, and then you check that with a luminosity distance. And then what you can see is that only for these curves, the whole scheme fits well, right? And it's and don't think that it's millimetric, it's statistical. It's statistical, okay? Now, this happens, if we live in an FLRW geometry, of course, no cosmologist will say the universe is perfectly FLRW. That's not true. Nobody, if you hear somebody saying that, you can throw a cake in his face. Nobody will say that. What people say is that at large scales, the geometry of the universe is FLRW with small perturbations, right? Small perturbations. At large scales. This is also not true at short scales, right? Short scales, you cannot say that a galaxy is like that, because galaxies have very large differences of density between the center and the outskirts, so cannot be described as a perturbation. But if you take very large scales, then the universe starts looking like something homogeneous with small corrections, right? So if we assume that, if we think, that's it, okay, we can all go now, the universe is known, we know the secrets of the universe, cosmology is closed, no more cosmology, we know everything, okay? Then you can say that only with the models with lambda non-zero explain supernova, right? Right? Well, if we assume this, if this is correct as long as the universe is like this, but who knows if the universe is? Well, let's say the universe is like this. Fine, excellent, very nice. Let's open champagne bottles and spend lots of money on grants and so on. That's very nice. But then somebody is over there asking nasty questions like, yeah, okay, what's dark energy? Because in order to explain that, you have to explain that you either need some sort of source that behaves like a cosmological constant, which has been called dark energy, or you have to explain that the cosmological constant is a fundamental constant. But there are theoretical problems with that, because first, a lot of models have been proposed with dark energy, to explain dark energy, as scalar fields and so on. All these models are plagued by a million inconsistencies. None of them, they are very bad models. They are called the quintessence things. They're all rubbish, bunch of rubbish. They are plagued with inconsistencies, because I can always say, for example, how can I explain this bottle? Well, I can always say that the Blue Angel brought it. But then I have to explain the physics of that Blue Angel, right? And then I say, no, it's a dark angel. So we call it dark, and then there comes a point, people, you should get tired of that. I don't understand why the economy is going so bad. Well, I invent some dark forces, and I say some evil forces, dark forces, and so that will convince a lot of people. But there will always be people saying, well, what are these dark forces? Please be specific. Show me proofs, how they are connected with this and that. Something similar is happening here. We can be very happy with proposing dark energy, the dark sector, quintessence, ghost fields, all sorts of exotic matter, and we are happy about that. But there comes a point you have to ask, well, Yeah, ghost fields. So what are they? What's the physical manifestation? Give me a prediction of how they are connected to particle physics, etc. And this is the key point. This is where we are all stuck, right? We are stuck in this. This is the way we can call things dark, and then all the empirical is explained. But then the problem is, what is this dark thing? Cosmological constant, so far, the best explanation, you can throw to the rubbish bin all dark energy models. These are total crap. But the cosmological constant